Antes que nada, antes de decir nada, tenemos la oportunidad de hacer un MPC acá mismo, así que les pido si pueden escanear esto. Durante la charla voy a explicar un poco más de qué va. Así que nada, dejo unos segundos más. Ok. Bueno. MPC. Privacy. Yeah, okay, I should do this in English. So, MPC is all about privacy. There's nothing else. Like, in zero knowledge, you can do perhaps like verifiable computation, but if you care, if you are trying to do or see like what can I use MPC for, like it's all privacy. Like privacy is your thing. You want to preserve your information. You want to protect your data from being misused, whatever. You're trying to protect something. And let's go through this very simple example. We have our friend Doge here, and he, of course, has some questions that he wants to ask to ChatGPT. So let's say he has a random question, like, what is a KZG commitment? Which I know that you already know about this, but yeah, let's say you don't. So you ask this to ChatGPT. What ChatGPT will do is he'll store this question, okay, let's say anonymously, so it doesn't store like this is coming from Doge, but let's just focus on the question data. It will store on this database, this big database, but every query is stored. And like, why? Because this data is very much important to train new models. Training new models is all about data. So data gathering is a big thing here. So yeah, let's say Doge here is sending personal information or corporate data. Yeah, all of this is going to be stored in this same database, and it's going to be used to train these new models. So if it's remotely possible that you can extract this data from this new model once it's built, then all your information is like pretty much available to everyone. So yeah, our friend here didn't do his homework. He just like gave away all this data. So let's try to use MPC to solve this. First, what is MPC? So plainly, MPC allows you to execute a function. In our example before, this function is this machine learning, this large language model with private information. So we focus on the Doge side of things, like the question is so private information. But we can also have the model as private information. So for ChatGPT, it's also important that its model like isn't spread around. Like they spend a lot of money trying to train this thing, and yeah, they will protect it, okay? So they won't give it away for you to run your queries locally. That will solve the problem, but they won't do it. So we can do an MPC here in which Doge inputs the query, like the question, and ChatGPT inputs the model data, like the structure and the weights. And like the whole answer of this only is received to Doge here. So even the output of a query could leak some information about the question itself. So this is important for like one party to receive the output only. So yeah, we solved this issue, but there are more things that we can solve. For instance, this specific use case of threshold cryptography. So we have two wallets with the secret key is like split it in half in this example, and we can sign a transaction using an MPC in which like this private key will not leave your devices. It will remain on your devices. You can run your MPC and just get this signed transaction altogether. You could also do like private list intersections. Let's say, for some reason, let's say our private music tastes are, yeah, private. We don't want to share them. Yeah, we don't want people to know we like Tool, for instance. So we just input this into an MPC, and then we can have like whatever we want, basically. We can have, you have a match with this person in which you both like the same bands, or you could have which bands you like. So that's totally programmable. To a more like real-world use case, we have the ads industry. So on this side, we have Amazon and Mercado Libre. They both have like this list of users who bought items, but Meta knows who did watch ads on these items. So if they can share, hopefully they're not doing this right now, okay? But if they can share this privately, they can track ads like efficacy or like these campaigns, like how well are these campaigns working on users. They will just see, okay, this person did buy this item, this person did see this ad, so that's a positive on that specific product. We can also run a trusted setup. So to run some zero knowledge protocols, we need this set of like secret stuff, secret numbers, which is what I made you scan at the beginning. So we can all contribute with our private information to build these secret numbers. This is a great use case. So in this use case, it's like if you could have all the secrets of everyone, you can reconstruct this, know the secrets, and make fake proofs. So this will throw everything away. With this, like everyone keeps their secret, and they can generate this trusted setup output to be used by these zero knowledge protocols. So okay, enough of use cases. Let's try to see how can we build this. So first of all, there's two main types of MPC. So one is specialized. These are protocols designed to build a specific function. And there are the generic ones, which like whatever function we can express as a circuit, we can run it, similar to like zero knowledge. We're going to go with this one, which is like the most interesting. Specialized are quite like reduced into what we can do with them. So circuits, same as zero knowledge, like they're just these fixed structures of like numbers and logical gates or arithmetic gates, which are fixed, and they look more or less like this. This is a basic circuit for a very simple operation. We have 5 inputs and a single output, and 3 addition gates and 1 multiplication gate. Very simple, but it's nothing more than this. Okay, so any circuit's going to be pretty much like this, but on a huge level. Of course, if we don't want to deal with circuits, we can use compilers. So compilers allow us to use these high-level languages that we can then transform into circuits, but we don't do that thing that's already done. So we can just write our program, more or less, in a high-level language. This is ZIRCOM. This is also used for zero knowledge. And then we can create our circuit. And we can create our circuit in a generic way. So this circuit is not binary, it's not arithmetic, it's just a set of inputs with operations. We can then use this with whatever MPC protocol we want to use it with. Now let's review secret sharing MPC. So this is like the simplest scheme of how to implement MPC. Secret sharing is based into dividing the secret. So the secrets here is like our inputs, our personal data. We're going to split this data so it's not recognizable in the outside. This data is going to be only rebuilt at the end of the process. let's see additive secret sharing. And the basic, example here is going to have one addition. We're going to have 2 inputs and 3 participants that are going to compute this. And we will need all the secrets to reconstruct these the inputs. So this is our structure. Like, we have 2 numbers, and those 3 computers are the ones that are going to compute this, like actually run the MPC protocol. What we will do now, we have two doges with 2 secrets each, with 1 secret each. Sorry, they want to sum their inputs, but they don't want to share it between them. So this is our secret. Let's generate these shares. This is our first secret. We're gonna choose 2 random numbers, and for the third one, we will base on this equation. So the total secret will be the sum of the shares, and so this gives us our last secret, which is 577. That's our last secret share. For the second output, we're going to do the same thing. We have our T1, T2, and T3. These are the 3 shares of our second secret. So we're going to distribute all of these numbers to the different computers that are going to run the computation. So as you can see, like, you cannot see anything about the original numbers. Like, these are pretty much random numbers to everyone. These are like these secret pairs, tuples, let's say. We have, like, each of them have a secret share of, like, an input. And this will allow them to calculate the computation locally. So they have everything they need to calculate the computation locally. So this is supposed to be a GIF, but yeah, I printed this, didn't remind. But they're thinking they're doing the calculation right now. And this is like the final sum of these shares. Yeah, pretty much random numbers all again. All they have to do is to sum these 2 numbers. What they have to do now is that they have to send these shares between each other to calculate the total. So if you can see the top equation there, like, the total is just the sum of each individual calculation. And this is like the correct calculation. So they all did this sum of numbers on secret share numbers, which they didn't know anything about, and they all make sense just once you have all the results put together. Now, this setup specifically assumes like an honest majority. So if in the first step they will share the secrets between each other, then they will know. Like, data won't be private. So we're trusting that at least one of them is honest in this particular case. What's important about this is that this final result, which in our case was just 1 addition, can be like compound. So you can do 1 addition, then 1 multiplication, then 1 addition, and then reconstruct all again. And this pretty much allows you to do any type of computation, any type of function that you can make into or put into a circuit and run an MPC with. We have to think about some extra stuff about this. So, like, the inputs can be pretty much any number. So it depends on your application. This can be troublesome because the result could leak some information. So if you're doing an auction and you can put a very high bid, like, participants could know how much money you have for this or who did win this auction. So even though, so the important thing here is that, like, everyone will receive the final computation somehow. So this is MPC only assures that the computation was correct and that the inputs were secret. So there's no, like, in the process, there's no leakage about your inputs, but the result could leak some valuable information. And performance, this is like the biggest drawback right now. So not so much regarding individual computations locally, but then once we have communication into this, it's like it gets hard to do some real use case MPCs. So let's say these two factors, what are they? So for communication, we have data volume. So this is just the total size of the messages, and the communication runs. So like how many back and forths you have between each party. And for computation, it's the processing, so the local processing of every operation. Of course, like as like the biggest the circuit's going to be more troublesome. But the main challenges here are participants. If you have a lot of participants, then this will take a lot of more communication. So this will limit the scalability of your protocol. You have transmission. So if you have low data transmission rates, like in a smartphone, let's say, that's also a problem to run MPC. And you have like latency. It's the biggest drawback. So the first model in additive secret sharing, that's very much real if you can have those three machines inside the same server running your function. Otherwise, it gets tricky. Unless we're dealing with like this trusted setup. So the trusted setup I showed in the beginning, this was this sequential MPC. So there's a line, and the first person in the line gets to download the last generated secret key. They input the randomness, and they upload it again. Then the next person in line does the same. So this sequentiality allows it to be used from your phone without any trouble. And yeah, this is it. I wanted to be very practical, just go through examples, and hope you had anything. Like, if you have any questions, you can ask. Okay, we're good. There's a list of resources and the link to the PSE Discord. Just, yeah, go through the resources. If anything, you have my contacts there. So, yeah, happy to discuss MPC. Thank you.